talk about beyond sparsity. So we are in sparse, and I'm trying to convince you we need to basically go beyond sparsity. So let me tell you why. Uh, Martin accused me, Martin Reinhardt, who keep saying crazy things. He accused me a few years ago saying, from the time I was a graduate student, I have only worked on arrays and I haven't done anything other than arrays. I said, yes, because arrays are really fun. First of all, arrays are very simple interface. Okay, you can do very simple things like lupo arrays, or things like in halide you can have implicit things, or really talk about Albert Einstein and saying we are doing einsums. So that seems cool to say to everybody else in there. Arrays are also very powerful. Lot of interesting mathematics can be represented using very simple ways in arrays. So it's a very powerful abstraction in here. And arrays are also very, very fast. By the way, later Willow is going to give a talk. I stole her slides, so you must see those slides again. So don't tell her, she's not here. So that's what the professors do, I says. If you look at last 50 years, or more than 50 years, most of the investment in hardware and software has gone to making arrays fast. Why do you have caches? Because it works very well in arrays. Why do you have prefetching? You fetch contiguous spaces in memory. Arrays. Branch prediction, vectorization is all about arrays. So we have done a lot of work on arrays in both in hardware and compilers, and now we are almost getting like kind of the roofline type performance you can get on arrays. So this is great. And arrays are everywhere. Arrays are in every possible programming language you can think about. Many languages, arrays is a very foundational data structure. In fact, arrays was the first important data structure introduced in the first language. Fortran introduced arrays. And if you think about programming languages as abstractions, Fortran abstracted many things, but things like control flow people knew already. They were in hardware, in assembly, and you did a little bit above. Arrays is, I think, the first thing that language introduced that's not in assembly. And say, okay, here's a new abstraction, multidimensional arrays. The interesting thing is, arrays haven't changed beyond Fortran. We introduced these arrays. We introduced in Fortran multidimensional dense rectangle spaces with integer grades of points. We did it in Fortran. We had it in Fortran. After whatever 70 years, if you do arrays, this is the only thing we do. Arrays is such a beautiful, simple, nice abstraction that everybody know. We should use arrays to do a lot more things. So I am going to talk about a few things. Obviously, we are in the sparse session, so we know we want to get rid of dense, we want to do beyond dense. And we know world is not dense. I'm not going to go through this. I think if you're in this room, probably you have seen this slide many times. So I stole it from Fred. Fred's slide deck at some point. So arrays go way beyond in here. So we know that. So I'm not going to dwell on that. I think we'll hear a lot about that. We want to go to sparse. Sparsity is why it's important. Because if you get data sparse, if the data is not that sparse, it's slow. We are doing a lot more work. But as sparsity increases, the amount of computation you have to do decreases, and you get execution time. This sparse matrix vector multiply. You have a break-in point about 65% sparsity. If you look matrix multiply, the break-in point is much lower because both the hardware people and software people have done a really good job in matrix multiply. Sparsity has to catch on a little bit more, but I think there's a lot of interesting hardware things coming on. I think if we do more compiler stuff, I think we might be able to move this bar a little bit to the side. But the interesting thing is, if you look at the spectrum, right now things like sparse neural networks is right in the cusp. If neural network people figure out how to get a little bit more sparsity, or ask compiler and hardware people try to figure out how to run sparsity a little bit faster, I think the entire world might switch to using sparsity in neural networks. It's a very interesting thing, I think, there. But that said, there are so many other problems that are hugely sparse. So you don't need to even think about it. These things you have to take advantage of sparsity. So starting with Taco that Fred started, we're looking at how to basically come up with very simple expressions like this kind of dense kind of expressions, einsums, formats, schedules, and basically generate code. We have done that. So I'm not going to go talk more about that. But one thing I want to mention is sparsity breaks a very foundational way of doing things in dense world. Most of the dense world is done by implementing these point-wise binary, I won't say binary operations very, very fast in libraries. We have matrix multiply, matrix vector multiply. Those things get implemented very low level, and then any complicated things you basically compose these things. You might lose a little bit by the memory bandwidth, memory performance, but not that much. Sparsity is very different. So this SDMM example in here, you are doing two matrix dense matrix multiply. You can do it very, very fast. There's all these libraries in here and do that. And then you're sampling it. And to get this value, obviously you have to do this matrix multiply, you have nothing else. But to get this value, you do nothing. So what you do is you sample you do this huge amount of computation to throw out most of it. So if sparsity is one place, you have to look at the entire operation as a unit. If you do this pairwise things, doesn't fail. So this gives even more cadence to do actually compile time solution. The graph I'm showing, the performance is Taco did by compiler, Egan did by hand, SDDMM the entire operation, and uBLAST said I have very, very fast routines. I will try to combine them, try to do SDDMM, but it is like orders of magnitude slower. So that's sparse dense. Then there are other things we can do in here. The world is not just always sparse and random. There's a lot of shapes in patterns in here. And later, Willow is going to talk a little bit more on how to expand in these kind of things. And so we need to deal with structure in sparsity. So let me give you a very simple example. So if you have this matrix in here, if you just represent it using like a compressed format, you can elate the zeros. You don't have to store the zeros. But if you look at this matrix a little bit carefully, there's more ones than zeros. So you can actually come up with a format that says, I am not going to store the ones. Ones are the implicit. I am going to store everything. I can get a little bit of a smaller matrix in here, representation in here, in memory. But if you look at even more carefully, there are a lot of runs in here. So one thing I can say is, when you replicate the value, replicate the last value ISO, that's run length encoding. And it's a very small extension to where we think sparse to get run length encoding going. In fact, if you do run length encoding in things like video and images, you can save a lot of space. Dense, you save nothing. Sparsity, only you eliminate one type of value with the zeros. In most cases, you get some savings. But using run length encoding, you can get a lot more savings. Compression community knows that. They have done that for a long time. But what they haven't done is actually operate directly on compressed data. In fact, if you do that, if you have runs of values in here, you can reduce the amount of computation you can do, and in fact, you can get a compute in here. So this is a really cool thing to do. So we need to do that. Another interesting thing we have looked at is when you look at arrays, it's rectangles. But the world has a lot of symmetry in here. The data is not rectangular. Data has triangles. It comes from sometimes data itself, like if you're representing a graph, basically bidirectional graph in here, you can do that. And also sometimes some computations produce outcome is basically symmetric data structure. So we can take advantage of symmetric in also both ways. First of all, you don't have to store this entire rectangle. And then you go to higher dimension, you get a lot less storage needed in there because it gets repeated in there. So you can we can save on storage. Also in compute, because first of all, if you are doing symmetric, you only have to load small part and it appears in multiple places. And also, if you are storing into a symmetric thing, you don't have to compute everything. You only compute that one region and it gets repeated in here. So this is really cool in there. You can do that. So the final thing I want to say is integer grids. Later we will hear from Jeon's talk in here. So the interesting thing is, when you work in dense region, dense requires data to be in all data points, all the points within the rectilinear space. You have to get that. And if you ever think about continuous, there's infinite amount of points. I can't represent infinite amount of points. So I have to have more of an integer type grid to represent that. But sparsity says, I'm not representing every point. I'm just selecting some points. I choose what points to represent. So if I'm choosing few points to represent, why do I have to select those points out of an integer grid? I can select those points from anything. I can have an infinite space of real points, and I can select the 1000 points. I do that. So if you do that, I can actually go into infinite space, and John will talk about, it's not about continuous points. You can do continuous regions. You can do all these cool things, and we can have a much more bigger description of arrays. This is, I think, really cool, because what it will give us is the ability to use this beloved abstraction that we know and love, and every undergraduate learns as in the first programming language class, and say, okay, look, use this abstraction. Now I can do a lot more out of this abstraction. I think this will be really fun things to do. And during the day, I hope to hear a lot more interesting ways of using array abstraction. Okay, let me stop there.